Mindsetters, happy Tuesday to you. I am Looney and joining us is Tracy.
Thanks, Looney.
How are you?
I'm very well, thank you. How are you?
I'm good, thanks.
Good.
So what are we doing for the Mindsetters?
Mindsetters, today, grade 10 physical science. We're going to be tackling the states of matter and the kinetic molecular theory. Very, very important as we look at the crucial theory behind what matter is made of and the different states of matter. So in this lesson, we're going to be using the kinetic molecular theory to consider properties of the states of matter, why things are solid, liquid, and gas, and what the properties of those three states of matter are. And then we'll consider what happens during phase changes. So something going from a solid to a liquid, or a liquid to a gas, or vice versa. Very, very important. There's lots of challenge questions. There's lots of things we want you to be thinking about. So I want to introduce the challenge question to you, but Looney, do you want to explain how the challenge question works?
All right. So Mindsetters, basically what happens is that we do have a challenge question on our notes. So what you need to do is that you go to our Facebook page, facebook.com/learnextra. There is the challenge question on our Facebook page. You answer it right under the post. There's the challenge question. You answer it right under the post. What we'll do is that in the last segment of the show, we will go through it. If you guys struggled with it, we will go through the challenge question and we will post the answer on our Facebook page as well. On that note, also hit us up on Twitter @LearnExtra. Visit our website for the notes, the videos, and the schedules on learn.mindset.co.za. And just a bit of information for all of you guys out there. As you know, February is the month of love. February is the month of love, so we want you guys to show the love, guys, and to show how you show your love. All you need to do is post your pictures on Facebook of items you love, of like your dog, like what your dog means to you, of someone special that you love. Tell us why that person is special to you. Tell us why you love that person, how that person shows love to you, and how you show it back. And we'll post it on our Facebook page, and we'll sometimes show it on TV and all of that stuff, and we'll just show the love to you guys because we love you and we're here to help you. So with that said, we are going to carry on with our lesson with Tracy, so I hope you guys enjoy it.
Thanks so much, Looney. So, Mindsetters, we want you to be thinking, because science is all about thinking and discovering and understanding the world around us. So, we need you to be thinking, and the way you do that is really to challenge yourself with answering these challenge questions. So, have a look at the question that I'm giving to you here. Hydrogen chloride and ammonia react. Now, those are two chemicals. They're going to react to form ammonium chloride, which is a white substance. And so, they've told us here that concentrated aqueous ammonia and concentrated aqueous hydrogen chloride are placed at two ends of a tube as shown below. So have a look at this picture. They've got some cotton wool with ammonia on the left-hand side and cotton wool with hydrogen chloride, HCl, on the right-hand side. When they react, they're going to be meeting somewhere. When they react, they release or form, what was it? They said a white substance, ammonium chloride. And that ammonium chloride we can visually see because it's a white color. The question is, how do the gases move along the tube? So you need to be thinking and explain that in terms of the kinetic molecular theory. So how do they move? That's first part. Where will they meet? And the answer here would be either A, B, C, or D. So make sure that you would be able to explain that. Where on the tube would they meet? And would then form the white cloud of ammonium chloride. The hint that I want to give to you is that ammonia has a relative molecular mass of 17 and hydrogen chloride has a relative molecular mass of 36,5 atomic mass units. So you need to think that through. Ammonia has a relative molecular mass of 17, whereas hydrogen chloride has a relative molecular mass of 36.5 atomic mass units. That's my hint to you. I need you to think about this and explain where they would meet, how they would move across along the tube. So, challenge yourself. Think about it and see what you can answer for that. Our summary. So, when we speak about the kinetic molecular theory, note it is a theory. It's a model that we want to use as we want to be able to explain what's happening in solids, liquids, and gases. And the theory basically says that all matter is made up of tiny particles. Okay? And those tiny particles could be atoms, if it's an element, or they could be ions. For example, sodium chloride would be in its ionic form, or they could be molecules. Some elements are molecules as well. Remember the diatomic ones, H2, Cl2, those kind of things. O2 would be molecules as well. But the basis of this is that all matter, if you went right down to the molecular level, would either be an atom, an ion, or a molecule. So basically all matter is made of tiny particles. Those particles, the second point, are always in motion, continuously moving. How will they move? Well, at high temperature, they're going to have lots of kinetic energy, so they will move faster. Okay? At higher temperature, the particles move faster. And heavier particles would have to move slower because they've got very big mass, so they're going to move more slowly. So think those through. All matter is made of tiny particles. Those particles are always in motion, constantly moving, and that motion depends on two things: the temperature at which they are, and secondly, the mass which they are made up of. And then the third point is that there are electrostatic forces of attraction between those particles, attraction and repulsion between the particles. So they're moving, and there are some forces between those. So kinetic molecular theory, basic idea is that all matter is made of particles, those particles are moving, and there are forces between those particles. If we go down to the states of matter, we can explain those states of matter by thinking a lot around what's happening inside those particles, with those particles. So solids, well, again, made up of tiny particles. Have a look. I've got the solids there. The picture of kinetic molecular theory, I should say, of solids. Those solids are still in motion, but they vibrate around a fixed point. So all the particles are moving, but they're moving around a fixed point. And what that's going to mean is that they would have a definite shape and volume. They're not going to take up the whole space of the container, but rather they would be at the base of the container and fill up that space. As opposed to liquids, those particles are able to move and slide over one another randomly and would fill the base of a container. Okay? So in a liquid state, those particles are able to slide over one another. Last picture I have here is for the kinetic molecular theory for gases. And gases have lots of energy and are able to move randomly in all directions. So significant movement in comparison to liquids and solids. There are very limited forces between those gas particles. They've got lots of energy, so they will hit against all the different parts of the container and fill up the whole volume of the container. So very important that you can explain the states of matter in terms of the kinetic molecular theory and the basis for that theory. If we now speak about what happens during a phase change. So imagine I've got a Bunsen burner, and let's give it a little yellow flame, or a candle or something, and that Bunsen burner is providing heat. There's a little Bunsen burner, and so we are thinking about heating a substance. That is causing an increase in the internal energy of the substance. So overall, heating a substance is always going to be adding in energy, internal energy. But where does that energy go? Well, it can go into two forms. Either it can go into kinetic energy, or it can go into potential energy. Now, by kinetic energy, I'm speaking about the energy that a substance has, or a particle has, because it's moving. Okay, so particles that are moving really, really fast, they have high kinetic energy. Particles that are moving slowly are going to have low kinetic energy. So kinetic energy, the energy substances have because of their movement or due to their movement. Potential energy is the energy inside that they have because of their state. So I would be able to observe a temperature. Now, temperature has a distinct definition, and you need to understand this very well. Temperature is a measure of the average kinetic energy of the particles. So, if I'm measuring, say, some boiling water, okay, or some water that's close to boiling point, I would measure that those particles, let's drop it down to room temperature. At room temperature, 25 degrees Celsius, the particles have maybe, say, a moderate amount of energy. But as I heat that, and it gets to maybe 50 degrees Celsius, those particles will be moving, on average, a lot faster. Now, we say average because not all the particles will necessarily be moving at exactly the same speed. But we're talking about the average kinetic energy, okay? So temperature is a measure of the average kinetic energy of the particles. And so, if we could increase the kinetic energy, so if we say heating something up, if we increase EK, the kinetic energy, that will result in an increase in speed. Remember, we said kinetic energy is about how fast those particles are moving around, at which the particles move, and that will in turn increase the temperature. So increased EK is going to be an increase in temperature, always. What happens during a phase change is something quite different. During a phase change, energy is put into the substance, yes, but you will notice, and you can maybe even do a practical on this, maybe if you even just get some ice melting at home, and you put some ice in a jug, in a glass or in a jug, or even just a little plastic cup, and you can measure the temperature. And you've got to obviously keep stirring so that you distribute the heat evenly. But what you would notice is that while the ice is melting, sure, it's getting energy from the outside, but it's not changing its temperature. And that's something very, very interesting, because you would think, but surely the ice is melting, it must be getting hotter. Well, it's certainly taking energy in, but its temperature is not changing. Instead, it is undergoing a phase change, which occurs as a result of the increase in potential energy. So no longer are we seeing an increase in kinetic energy, which it would then be observed as an increase in temperature. Rather, the energy that's taken in is going into a change in the potential energy of those particles. They gain enough energy to overcome the forces of attraction between them and break away from each other. So the temperature is going to stay the same. Temperature remains constant during a phase change. All the energy that's taken in goes into gaining potential energy so that those particles move and are able to overcome the forces of attraction. Now, this might be counterintuitive, but you need to think it through. Energy is going in, but where? It's going certainly into the internal energy, but where in the internal energy? Into changing its phase, so into potential energy, to allow those particles to move further away from one another. So if they were a solid like ice, they would be able to slide over one another into a liquid phase, and that's how you would observe melting. In comparison, once all of it has melted and you keep heating the substance, it will continuously then go into changing the temperature, and it will heat. The water now liquid water will start to heat up. So thinking this through, it's incredibly helpful to remember whether you're measuring temperature or whether you're measuring and observing a change in kinetic energy, or whether you're looking at a phase change. And in our next segment, we will be looking at and considering a cooling curve where you will actually see the temperature remains constant. So that's it for the first segment, and I hope that's really helped give you a short summary of the kinetic molecular theory. In our next segment, I want to challenge you to go during this break, go do the challenge question, and also go and find out those test yourself questions. There are plenty of questions I've put out there as test yourself, and I want you to answer them as much as you can. Thanks, Leni.
All right, Mindsetters, we are going to take a short break, but let me remind you again, please post all your pictures of Show Your Love. Remember to hashtag it, Show Your Love. You must be in the picture as well. So post your picture. You must be in the picture with your special someone for this month of love, or a special thing, say for example your bicycle, your puppy, or anything that makes you happy, guys, and tell us why it means so much to you. Post it on our Facebook page and you might just see yourself on TV, man. So we are going to take a short break, so do stay tuned. Welcome back, Mindsetters, from that break. Before we start, quick shout out to Katie, Dumisani, Sizwe, Danica, and Mola. Thank you so much, guys, for tuning in. Thank you for enjoying the lesson. Let us carry on.
Thanks so much, Leni. So, Mindsetters, we said we've spoken about the kinetic molecular theory. Now I want us to start challenging ourselves with some interesting questions. So, a graph below. Now, you have to be able to interpret graphs. Graphs are so important to science because, remember, maths and these kind of things is the language in which we often communicate. And so, to interpret the picture, the graph is so very important. The graph below indicates a cooling curve. Now, that's helpful because what it's saying is that we're starting at a high temperature and we're going to be cooling it down, okay? And now we are cooling it down. The temperature of a substance as it cools over time. So, have a look at the picture. We start off at approximately 120 degrees Celsius. Obviously, you need to read off a graph. And here I've got a sketch graph. But if you were given a test or an exam question, you would be able to read more distinctly off graphs with lines on the grid paper. It starts off at 120 degrees Celsius and it cools right down to about 15 degrees Celsius down there. So over time it's cooling, but what I need you to recognize is that over the time it's going through some possible phase changes, and we can identify that because of those horizontal lines. Remember, during a phase change, the temperature remains constant. So here, definitely, there's a phase change occurring as all of that substance changes phase, and so the temperature is remaining constant. Now I'm going to take that line away so we can hopefully come and answer some questions. Identify any phase changes occurring in the substance. So that's what they're going to be asking us to do. So I'm going to start some colors on this graph and write up what's happening. I'm going to start there and identify that is a gas. How do I know it's a gas? Well, I said to you it's undergoing at least 2 phase changes because there's a horizontal line which is an indication of a phase change. There's another one, and there's a third one, which we'll come to that a little later. So at the top here it's a gas, then it's changing phase, there it's a liquid, all a liquid. Here it's changing phase again, and so here it must all be solid. Now that's quite useful. Again, I'm now going to change color so we can identify. From B to C, it's needing to change from a gas into a liquid. So this is going from gas to liquid. Okay, and we need to name that, but we'll name it in a moment. Then from D to E, it's going here liquid to solid, and we need to identify what phase change that is as well. So from B to C, what phase changes that gas to liquid? We would say it's condensing. So this must be condensation. And I think I need to give myself some space and write down here. B to C, it is condensation. condensation. It is going from gas to a liquid. The next one, there's going from liquid to solid, and that would be freezing. So that was D to E on the graph. DE, because recognize, they're saying identify phase changes, it would be freezing. And that is going from a liquid to a gas. What is the boiling point of the substance? Okay, now boiling point is the temperature at which something goes from a liquid to a gas, or vice versa, a gas to a liquid. It could also be called the condensation temperature, but we usually speak about the boiling temperature, the boiling point. It's a specific temperature at which that substance undergoes a phase change between liquid to gas or gas to liquid. So, as we look at this graph, where it would change if I was heating this if I was reading from GF backwards, it would change from a liquid into a gas from C to B. So that temperature, I'm going to need to read off the graph, and I'm going to take my little dotted line and line it up there. So let's see if we can undo that little line, and I'm going to try and make a little dotted line. You would dot that line across and read, it's definitely 100 degrees Celsius. Now, water has a boiling point of 100 degrees Celsius, but we can't just assume that this thing is water. We'd have to read off quite a few more points before we could identify that. Identify the region on the graph when the substance is all a liquid. Okay, so where on this graph is it all a liquid? Well, from B to C, it changed from gas to liquid. From C to D, it should all then be a liquid, and that's how we would notice the temperature is dropping as this thing is cooling. But remember, it won't drop until all of that substance has changed. So it must be from C to D. So my answer here must be CD. It is all a liquid. Then what is the temperature of the room? Okay, we'll come to that in a moment. Have a quick look here. What is the temperature at which this thing freezes? At which this thing all becomes a solid? Well, again, I'm going to dot a line across. It's approximately maybe 45 degrees Celsius, 100 degrees Celsius, I'm not quite sure. It's 45, maybe 50 degrees Celsius. It's about halfway between 15 and 100, so it's approximately there. That's why I can tell it's definitely not water. What temperature would water freeze or solidify at? Surely at 0 degrees Celsius. So this is definitely not water. But now having a look at our graph, we've identified it was a gas, it's cooled and it's condensed, so it's become a liquid. The liquid has then cooled further and has become a solid through that phase change, and now it's all a solid. But what is happening at this point down there, F to G? Are there any further states that this thing could go into? No, there aren't. It's all already a solid. So why would it be leveling out? Well, think this through. Definitely, the temperature of the solid has dropped to a point, and then it has remained the same. So we must be able to say, well, surely the environment that this is in, it's cooling to its surroundings. It's not going to drop any lower than the temperature that the room is in. Okay, so from F to G would be the temperature at which the room is at. So what is the temperature of the room? Well, it must be at point F to point G, and we need to answer the question by reading off a temperature, and so I'm dotting that line across. Sorry, it wasn't a particularly straight line. Let's see if it will allow me to take it back. Taking that line right across, it should be 15 degrees Celsius. So that must be the temperature of the room, and I must answer here 15 degrees Celsius, and that is at the point Fg. Okay. Why? Because the solid temperature, all are solid, so it's not changing phase again, but it's cooling to its surroundings, the same temperature as the rest of the room. All right, we've got one more question for the Improve Your Skills. Stephen wants to know why his fingers often stick to the ice or to the ice tray when he takes ice out the freezer. And I'm sure that you've experienced this before. You go lift something out the freezer and your fingers start sticking to it. Why is that? Or even if you hold a block of ice, your fingers sometimes stick to it. Explain this to him using your knowledge of the kinetic molecular theory. So, once again, we're wanting to talk about the kinetic molecular theory and the states of matter to explain why his fingers would stick to the ice as he removes it from the freezer. Well, this is an interesting question. You would recognize that your hands are relatively warm. Okay? Certainly relatively warm, much warmer than the ice as it comes out the freezer at maybe below 0 degrees Celsius. And so your hands are going to provide lots of energy directly to the surface of the ice and will melt the ice at that point. But because the rest of the ice is so cold, that energy will quickly be taken away from the surface around that block of ice. And so, although the ice would have quickly melted, there will be moisture, it will immediately refreeze. And so your fingers stick because of the refreezing. So let's jot a few points down. Number one, we can say his hands are warmer. Obviously much warmer than the ice surrounding it. And so that would cause the ice to melt. Directly at that point where he's holding it, the ice will melt and will result in some moisture. Okay? When I say melt, it would go from a solid to a liquid. Remember, the question asked us to explain this in terms of the kinetic molecular theory and states of matter. So it's very helpful to make sure that you're linking in the states of matter. So the solid ice block starts to melt because his hands provide more energy for those particles to overcome the force of attraction and change state or change phase. So during that melting, there will be more moisture as the energy his hands provide will allow them to overcome the force of attraction and change phase. But then that melted ice, the liquid, will change back into a solid. Why? Well, because very quickly, maybe we need to say here, very quickly that moisture will change back into a solid and so will freeze because of the high temperature difference. Okay? Because his hands are so much warmer than the ice, the melted ice will quickly refreeze. Go back into the solid state. So it's going to be liquid goes back to the solid phase. The reason for that is that energy is very quickly taken to the other ice particles, and so it's going to very quickly refreeze. Now, maybe we should write that last point as energy is transferred or given away to the neighboring particles. Now, thinking this through, I think it's quite valuable to think about the fact that the temperature difference has resulted in a phase change, but because the temperature difference is so extreme, the rest of the ice is still so cold, it will take up a lot of that heat energy and will result in it refreezing. And that's why when you take ice out the freezer, or when this individual took ice out the freezer, it started to freeze against his hands and became a solid. We're going to take a short break, and when we come back, we're going to focus on that challenge question, and we'll look at some of the tests yourself. So I really hope that by now you've had a look through that challenge question. If not, take an opportunity in this break. Leni, over to you.
Mindsetters, we are going to take a break. I see a lot of you have answered the challenge question, so we'll look through that right after the break. So don't go anywhere. We'll see you straight after this. Welcome back, Mindsetters, from that break. Thank you so much to all the guys who answered the challenge question. Shout out to Retabile Dumsani, and then it does funny things. Retabile Dumsani, Jack, and Progress. Some of you got it right, some of you didn't. So we are now going to help you with the challenge question. Tracy.
Excellent. Well done, Progress and Landman Retabile.
Yes.
Brilliant. The answer is D. You're absolutely right. But let's think about why and make sure you give a full explanation in terms of why. Hydrogen chloride and ammonia react together to form this ammonium chloride, a white substance. And so I'm going to just, on my picture here, draw in a little white cloud. Okay? Obviously, it's within the tube, but I don't want to commit to whether it's over here, or over there, or over there. Okay? But it's a white cloud. What is in that white cloud? It is ammonium chloride. Okay? So inside this cloud is made up of, I'm not going to have enough space there, so NH4Cl. Somewhere along the tube, that substance is going to be formed. But why? Well, let's answer this in a few different steps. How do the gases move along the tube? It's based on the understanding of diffusion. Let's just quickly start this again. It's through diffusion, and diffusion is the movement of gases from a region of high concentration to a region of low concentration. And think about it, particles are always bumping into each other, particularly gases, always bumping into each other, and will move randomly. But where there are lots of them packed closely together, they're going to be bumping into each other lots, right? And so eventually they will spread out. So the aqueous ammonia will diffuse that way. The hydrogen chloride will diffuse that way. So diffusion is meaning that those particles are in constant motion, and because of that constant motion, and if you were to answer this, it's according to the kinetic molecular theory, we know that they will move randomly in all directions. Okay? Because they're moving in all directions, they will eventually go down the tube from high concentration to a low concentration. So therefore, they move down the tube. That's the first part of this question. The question was, how do they move? Well, we've definitely answered that. And we've used the kinetic molecular theory as our framework. The fact that all particles are in motion, they will move from a high concentration to a low concentration down that tube. Then the second part of this question. where will they meet and form the white cloud of ammonium chloride? Now, ammonium chloride is that white cloud we've had there. Where will they meet? Well, where is going to refer to, it will depend on the speed of that diffusion. What controls the speed of diffusion? Well, firstly, the temperature of the substances. Temperature means, high temperature means particles are moving very, very quickly and therefore will diffuse very quickly. Low temperatures, the particles will move more slowly and so therefore will diffuse more slowly. Is there a difference in temperature here? No. The question had nothing to do with temperature. They didn't say anything that was a temperature difference between either of them. So the temperature, but in this case, there was no difference in temperature. So we can't make any statement about a difference in temperature here. What else controls the speed at which particles move? Certainly their mass. Remember we said heavier particles move more slowly and smaller, lighter particles will be free to move more quickly. So heavy particles move more slowly. Lighter particles will move faster. Okay, will move a lot faster. So our focus here is that the mass of these particles. And I gave you a hint about the mass of the particles by saying, right at the bottom here, hint, the relative molecular mass of ammonia is only 17 atomic mass units. And for aqueous hydrogen chloride is 36.5 atomic mass units. So which one is heavier? Well, it's definitely this guy, the hydrogen chloride. He's going to be, I say he very loosely, those particles will be moving more slowly. So as they go along, they're going to be going more slowly, whereas the ammonia will be able to travel very quickly and will probably reach the hydrogen chloride somewhere around about there. Okay? So if I take that away, it will be D as our answer because the heavier hydrogen chloride particles will take a lot longer to diffuse along that tube as opposed to the lighter, with much less mass, the ammonia molecules will travel much faster and so will travel a lot further along that tube in the same amount of time. So our answer here is therefore meet at D. Have we answered the whole question? Where will they meet and form the cloud? They will meet at D. Now, this is a very, very interesting question because it brings in lots of understanding of what's happening at each of those different points. Okay? Particles will diffuse, move from a high concentration which at either ends of the tube, along the tube. Where will they meet? Well, the ones that are traveling fast will be able to travel a greater distance than the ones that are traveling slowly because they have a heavier mass. So therefore, they will travel more slowly. I hope that's really helped you, and I hope that made you think about the kinetic molecular theory. So well done to those of you who got that right. That was brilliant. We've got quite a few test your knowledge questions, or test yourself questions, and I want us to try and go through some of these answers, and I'm sure we'll also have time to answer some of your questions. So please do post your questions on Facebook. Select the most correct answer from the options given. Write on only the correct letter. Question 1. According to the kinetic molecular theory, matter is made up of, well, this is a simple one. Crystals? No. Molecules? Sometimes, but what about atoms? Atoms would be true as well, so no. Small particles in continuous motion. That looks true. Energy? Definitely not. So According to the kinetic molecular theory, matter is made up of particles in continuous motion. That's our answer. Question 1. Question 2. Select the most correct answer from the options given. Question 2. Which of the following is not a state of matter? Key word there, not. Watch out for that because it can be quite a trick, the negative of those. So, state of matter. Solid is definitely a state of matter. Metals? No. Liquids are a state. Gases are a state. So, metals are definitely not a state of matter because not all substances are metals. Remember, a metal is an element on the periodic table, or a number of elements would fall into that category of metals. Question 3. When ice melts, its temperature increases? No, its temperature doesn't increase. It may increase once all of it has melted, but it won't increase while it is melting. Because while it is melting, and I think, Luni, we had a question on this.
Yeah.
While it's melting, it's going through a phase change. And I know this is counterintuitive, but during that phase change, all the energy that's going in, if you had a little Bunsen burner or a little candle or something underneath, heating a beaker of ice, the temperature, the increase in the energy is not going into temperature. Rather, it's going into increase in potential energy, which is giving particles more energy to overcome the force of attraction that would normally be holding them in the crystal, in the solid form, in that solid lattice structure. So instead, now they're able to overcome those forces of attraction and slide over one another. And so no, it's not going to increase temperature or decrease temperature for that matter, but rather when it's melting, the energy is going into a change in potential energy, an increase in potential energy, which would then be seen as a phase change. So when it melts, its temperature increases? No. Its temperature decreases? No. It releases heat to the surroundings? Definitely not. If anything, it's taking up heat from its surroundings, not releasing heat. Its temperature remains constant. That is true because it's undergoing a phase change, which means that it's going to increase potential energy. An increase in temperature would be observed when particles are changing their kinetic energy. Okay, overall the average kinetic energy of the particles. And these particles aren't necessarily moving any faster, but rather they now have a higher potential energy, which means they have more energy to overcome the force of attraction that are holding them in place. Question 4. A phase change from a solid directly to a gas is called what? Well, this is an interesting one because we don't often see this. But if something completely almost skips the liquid phase, you've got, it wouldn't be evaporation because evaporation is a change in phase from a liquid into a gas. But remember that evaporation is quite different to boiling. So watch out for that. Make sure you know the differences. Evaporation can take place at any temperature and boiling has to happen at a specific temperature. So watch out for those. Evaporation only happens at the surface of the liquid, whereas boiling happens within the liquid as little bubbles are formed of that vapor as it goes into the gaseous phase. Sublimation, well, that's an option. Condensation is from gas back to liquid, and freezing is from liquid to solid. So our only option here is B, sublimation, going from a solid directly to a gas, skipping the liquid phase. Question 5. Water is spilled on a countertop and evaporates. The drop in temperature of the remaining water. So I want to almost sketch this for you. If you've got water, a little droplet of water spilled on a counter surface, okay? Those particles that are at the surface are going to be able to evaporate and go into the gaseous phase. While they're doing that, they're going to have to take up energy from their surroundings, but it's only those ones that have high enough energy to break away from overcome those forces of attraction between them and their neighbors that will be able to go into the gaseous phase. So remember, to change phase, it means to overcome the forces of attraction that is holding it in that phase. So here, the particles at the surface are able to escape. What it means is that those ones that are left behind will on average have a lower energy, lower kinetic energy. So let's go through. Water spills on a countertop and evaporates. A drop in temperature of the remaining water is due to. Now, always a temperature change, you're thinking change in kinetic energy, EK. And that change is due to the fact that the remaining liquid gains internal energy. Gains is definitely not right. The higher kinetic energy of the remaining water particles, no, because we are seeing this as a drop in temperature, which means it's going to be a lower kinetic energy. So that's not true either. The vapor molecules that escape have a higher average kinetic energy than the liquid that is left, the molecules that are left in the liquid. That is true. And no, we wouldn't see the drop in temperature with a phase change. So option there, C. And I think that's the last question of the test yourself, question 5. Mindsetters, I need you to be always thinking about what questions you can ask with kinetic molecular theory, and I'm sure you've got questions. Looney, go for it.
Some questions from Twitter for a change, at Tomlinson, okay, is asking, does diffusion only pertain to gases?
Diffusion mostly occurs in gases. It certainly can't occur in solids, but gases and liquids can diffuse. If you think about it, if you put a drop of food coloring into a beaker of water, over time, that food coloring will spread around throughout the whole liquid, and so would spread out. And that's also an example of diffusion. So liquids and gases, but not solids, because remember, solids are held in that fixed structure.
Okay, and then Tepe is asking, why is there a melting point for a substance in a gas state, because gases only change phase by condensation or deposition?
So why is there a melting point?
Yes, for a substance in a gas state.
Okay, it's not that it's saying it's a melting point for a substance that is necessarily in a gas state, but all substances have a melting point and a boiling point. So possibly in a question they could give you a table and give you the melting point of the substance and a boiling point of a substance, and say at whatever temperature is the substance a solid, a liquid, or a gas, and you would be able to go and read off where it's going to be, if it's going to be in the gaseous phase, or if it's going to be in the liquid phase, or if it's going to be in the solid phase. It goes back to a specific temperature for a specific substance to change phase. But a gas doesn't have a melting point. A substance has a melting point. So it's not that the gas specifically is going to melt. It will first have to cool and condense, and then it will eventually get to its melting point.
All right, and then Samkelo Atol is asking, does it happen that the water... Okay, no, let me rephrase this. Is it possible for water to be in a solid state, but it's hot?
Is it possible for water to be in a solid state, but it's hot? No, because if it's hot, so say 25 degrees Celsius, all of that energy that's gone into it will have already caused it to melt. So no, it can't be a solid at 25 degrees Celsius. Or for that matter, it can't be a solid at 100 degrees Celsius. So no, not possible.
All right, one more. Balesa Makuru, I don't get how phases can change without an increase in temperature.
Okay. This is a very hard question to think through. I know it can be challenging, and that's why we spent so much time on it way back when. I'm going to jump across to our summary, which was quite a lot further back. But the focus here is that when you heat something, you can either give it kinetic energy or you can give it potential energy. You're not giving them it both at the same time. So the temperature, we know, is measuring the average kinetic energy of the particles. So when you're heating something and it's changing phase, where is that energy going to? Is it going to go into kinetic energy? No, it's not. All of that energy will go into potential energy to allow the particles to gain enough energy to change phase, to overcome the force of attraction between those particles. I really hope that's helped, and I hope that's answered some of your questions. Mindset is keep thinking, keep questioning. It's so, so important because we want you to develop deep understanding in physical sciences. That's all for me for today. So keep thinking, keep well, go well, and God bless. From me, Tracy, signing off for now.
Thank you, Tracy, so much for that great lesson. Mindsetters, thank you so much for tuning in. Remember to always show the love for the rest of the year, not just on Valentine's Day and in Feb. We love you so much, and thank you for tuning in. Goodbye from us.
Between those particles, attraction and repulsion between the particles. So they're moving, and there are some forces between those. So kinetic molecular theory, basic idea is that all matter is made of particles. Those particles are moving, and there are forces between those particles. If we go down to the states of matter, we can explain those states of matter by thinking a lot around what's happening inside those particles, with those particles. So solids, well, again, made up of tiny particles. Have a look. I've got the solids there. The picture of kinetic molecular theory, I should say, of solids. Those solids are still in motion, but they vibrate around a fixed point. So all the particles are moving, but they're moving around a fixed point. And what that's going to mean is that they would have a definite shape and volume. They're not going to take up the whole space of the container, but rather they would be at the base of the container and fill up that space. As opposed to liquids, those particles are able to move and slide over one another randomly and would fill the base of a container. Okay? So in a liquid state, those particles are able to slide over one another. Last picture I have here is for the kinetic molecular theory for gases. And gases have lots of energy and are able to move randomly in all directions. So significant movement in comparison. Note it is a theory. It's a model that we want to use as we want to be able to explain what's happening in solids, liquids, and gases. And the theory basically says that all matter is made up of tiny particles, okay? And those tiny particles could be atoms, if it's an element, or they could be ions. For example, sodium chloride would be in its ionic form, or they could be molecules. Some elements are molecules as well. Remember the diatomic ones, H2, Cl2, those kind of things. O2 would be molecules as well. But the basis of this is that all matter, if you went right down to the molecular level, would either be an atom, an ion, or a molecule. So basically all matter is made of tiny particles. Those particles, the second point, are always in motion, continuously moving. How will they move? Well, at high temperature, they're going to have lots of kinetic energy, so they will move faster. Okay? At higher temperature, the particles move faster. And heavier particles would have to move slower because they've got very big mass, so they're going to move more slowly. So think those through. All matter is made of tiny particles. Those particles are always in motion, constantly moving, and that motion depends on two things: the temperature at which they are, and secondly, the mass which they are made up of. And then the third point is that there are electrostatic forces of attraction.
What's up, Mindsetters? Happy Tuesday to you. I am Looney, and joining us is Tracy.
Thanks, Looney.
How are you?
I'm very well, thank you. How are you?
I'm good, thanks.
Good.
So what are we doing for the mindset is?
Mindset is today, grade 10 physical science. We're going to be tackling the states of matter and the kinetic molecular theory. Very, very important as we look at the crucial theory behind what matter is made of and the different states of matter. So in this lesson, we're going to be using the kinetic molecular theory to consider properties of the states of matter, why things are solid, liquid, and gas, and what the properties of those three states of matter are. And then we'll consider what happens during phase changes. So something going from a solid to a liquid, or a liquid to a gas, or vice versa. Very, very important. There's lots of challenge questions. There's lots of things we want you to be thinking about. So I want to introduce the challenge question to you, but Looney, do you want to explain how the challenge question works?
All right. So mindset is basically what happens is that we do have a challenge question on our notes. So what you need to do is that you go to our Facebook page, facebook.com/learnextra. There is the challenge question on our Facebook page. You answer it right under the post. There's the challenge question. You answer it right under the post. What we'll do is that in the last segment of the show, we will go through it. If you guys struggled with it, we will go through the challenge question and we will post the answer on our Facebook page as well. On that note, also hit us up on Twitter at @LearnExtra. Visit our website for the notes, the videos, and the schedules on learn.mindset.
Somewhere, when they react, they release or form, what was it? They said a white substance, ammonium chloride. And that ammonium chloride we can visually see because it's a white color. The question is, how do the gases move along the tube? So you need to be thinking and explain that in terms of the kinetic molecular theory. So how do they move? That's first part. Where will they meet? And the answer here would be either A, B, C, or D. So make sure that you would be able to explain that. Where on the tube would they meet? And would then form the white cloud of ammonium chloride. The hint that I want to give to you is that ammonia has a relative molecular mass of 17, and hydrogen chloride has a relative molecular mass of 36,5 atomic mass units. So you need to think that through. Ammonia has a relative molecular mass of 17, whereas hydrogen chloride has a relative molecular mass of 36.5 atomic mass units. That's my hint to you. I need you to think about this and explain where they would meet, how they would move across along the tube. So challenge yourself. Think about it and see what you can answer for that. Our summary. So when we speak about the kinetic molecular theory,
.co.za, and just a bit of information for all of you guys out there. As you know, February is the month of love. February is the month of love, so we want you guys to show the love, guys, and to show how you show your love. All you need to do is post your pictures on Facebook of items you love, of like your dog, like what your dog means to you, of someone special that you love. Tell us why that person is special to you. Tell us why you love that person, how that person shows love to you, and how you show it back. And we'll post it on our Facebook page, and we'll sometimes show it on TV and all of that stuff, and we'll just show the love to you guys because we love you and we're here to help you. So with that said, we are going to carry on with our lesson with Tracy, so I hope you guys enjoy it.
Thanks so much, Looney. So, mindset is we want you to be thinking, because science is all about thinking and discovering and understanding the world around us. So, we need you to be thinking, and the way you do that is really to challenge yourself with answering these challenge questions. So, have a look at the question that I'm giving to you here. Hydrogen chloride and ammonia react. Now, those are two chemicals. They're going to react to form ammonium chloride, which is a white substance. And so, they've told us here that concentrated aqueous ammonia and concentrated aqueous hydrogen chloride are placed at two ends of a tube as shown below. So have a look at this picture. They've got some cotton wool with ammonia on the left-hand side and cotton wool with hydrogen chloride. Hydrogen chloride, HCl, on the right-hand side. When they react, they're going to be meeting some